Thank you for joining us for our chromatography webinar, Mass-Directed Purification. If you have any questions during the webinar, please utilize the chat or Q&A functions within Zoom. All questions will be answered at the end. This webinar will be recorded and a video will be made available in the next few days. Our presenter today is Todd Anderson, Global Chromatography Specialist. With that, I will turn it over to Todd.
Hey everyone, I just wanted to thank you for joining us this morning. I'm coming to you live here from nice cold Lincoln, Nebraska. We had some snow last night, so it made it interesting getting in here this morning. So today I'm just going to try and go over some of the things that I've experienced and some of the things that I can possibly help you with in trying to purify some of your hard-to-detect material. We'll go over the different types of detection very briefly in the beginning, but ultimately try to focus on some of the problems that you may or may not be having with your mass spec. So anyhow, let's go ahead and get started. So for those of you who are new to us, Teledyne, as I mentioned, is located right now in Lincoln, Nebraska, where I'm at currently. So if you'll see on the map here, you can see my little cursor floating around. It's a little delayed due to technology, obviously. And I'm located here in Pennsylvania, Philadelphia, Pennsylvania. So we can go ahead and start looking at the different types of chromatography. And I have a little bit of a slight lag here, I think, between my computer and the one that you guys might be seeing. So bear with me. We can go through the different types of chromatography. So you have flash, which is usually for not quite as pure of a material, larger amounts, up to milligrams to gram quantities. Usually it's going to be lower pressure, lower quality purifications. What I'm going to focus on here is for the Prep HPLC right here. So we're going to be looking at the systems we currently use for our higher resolution systems are anywhere from typically 3 to 150 mils per minute when we're using them for mass spectroscopy. Having said that, later on when we do get into the mass specs, actually all the detections for that matter, we can incorporate the detection schemes on any one of the three systems that you see down here at the bottom. So at the bottom you see our CombiFlash NextGen, the EasyPrep, and the ACCQPrep HP150. Most of the work that I have is going to be generated on a CombiFlash EasyPrep, but I have some data that's been done on the ACCQPrep as well. And my screen is locked up. Oh, there we go. So the ACCQPrep 150 is the one that I typically focus on because we can get the best resolution out of it. The flow rates are typically 1 to 150 mils a minute if you're using UV or ELSD based, well, yeah. UV and ELSD based, I'll leave it there. Mass spec, because of the delay volumes, we typically try and run it a little bit faster at about 3 mils a minute. So what are the parameters that we try to look at when we do try and achieve higher purities? We're going to be looking at stationary phases, and we've had many online presentations that are very similar to mine that we've done before for both solvents and columns. As you can see, we also get into method development, which I'll bring a little bit of that into this discussion as well. But if you want to go online and, as you see down at the bottom, you can take a screenshot or take a look at it right there. That is actually where we have all of our seminars and webinars. Sharon helps us out quite a bit with making sure that they're all up to date relatively quickly after they've been posted. So probably in 2-3 days, you know, maybe a week at the tops. This should be online in that same location. But there are also seminars on there as well about maximum loading, how to maximize your capacities. My last presentation was done on how to efficiently load up chromatography without destroying your resolution. So what I'm going to focus on today is this down here at the bottom. And we're going to be doing the detection and collecting pure peaks. So as I go forward through, I'm just going to start with the detection. So we have the availability of a 200 to 400 nanometer detection as a standard base on our instruments. So what I would like to show you here is we have two different wavelengths, 214 and 254, our standard two-wavelength detection parameters, and this can be seen on all of our products. This is on an ACCUPrep, I know, because it has the green background. So the other option is also 200 to 800 in case you have dyes or something that you might not be able to see your compound in the 200 to 400 region. I have recently had a lot of customers starting to ask me more about maybe a third wavelength. We can possibly do that. So if you bring up a chromatogram, as you can see down here, a lot of our customers are not aware that we can actually do this. So as you'll see, there's two buttons on your data processing where you can see the UV or MS. These are also available during your live running of your samples. So if you bring these up and you select on a peak or a particular retention time of interest, we can actually get a full UV spectrum of that. So typically most people will do 214 and 254, but what if there's something out here that might be a little bit higher, some place that you might want to isolate just a single wavelength that is similar to the compound of interest, but not to the other impurities that might be near there. You can also choose that as a third wavelength. I'm going to show you how to do that here. So we would just click on this radio button, and it brings up this option. So what I've been working with customers lately is we're doing peptides and protein purifications. We will have them use a 280 wavelength. So we would change this first minimum to maybe 278 and the maximum to 282. So if we put that range in there, it effectively gives us a third wavelength that we can do either monitoring or fraction collection based on that third wavelength. Having said that, we can also bring in, if you don't have a mass spec, we can bring in an external detector. So in the past, if I've done some chiral chromatography where maybe an optical rotation detector or refractive index detector might be efficient for what you need to get done. You could also use fluorescence if you wanted to bring in a third-party fluorescence detector. Or we can also use conductivity and pH meters. And most people that do standard reverse phase chromatography are going to say, well, why do you need those? I particularly don't use them, but I know that there are some instruments out there and there are some bioprotein and peptide people who actually like to monitor that as a history issue. So we can always bring them in as an additional channel onto our systems if you need it to. With our integrated ELSD, what we do is we actually incorporate the LSD into all of our instruments. So you don't have to worry about a third device sitting on the side beyond your autosampler and your instrument. So it gives us quicker response, and it gives us an ability to actually get additional data. If you have a peak that doesn't have a very strong chromophore, maybe you might get an ELS response from it. The other thing that we can also use with the ELS detection is it'll help us to determine which of our materials actually have a real mass to them. If you have a solvent or some sort of a very small anomaly in your synthesis or your reaction, you might see a very strong UV response, but it might not actually be a real solid amount of material. So you might not see this green trace on your particular chromatogram. So this will help us to define how much material is actually there, typically by weight. I don't like to say by mass because, of course, that's going to be a couple of the next slides down. But anyhow, moving on, the nice thing about our systems is we can actually put a very broad range of chromatography onto our ACCUPrep system, anywhere from 2 to 3 mils a minute, all the way up to 150 mils a minute. Our largest flow rate here, obviously, is 42.5 that we tested. But across the entire range, if you look at all of these individual chromatograms, there is a peak overlap on all three detections, whether it's the UV1, UV2, or the ELSD. We can also do the same thing for mass spec. So that's where I'm going to get into mass-directed purification. This is where I'm going to spend most of the talk today. So if we choose anywhere from 10 to 1200, we have one mass spec unit that does that very nicely. If you do require a mass charge a little bit higher than that, maybe up closer to 12, 1500, then maybe we might want to go to our L version. The S usually is pretty sufficient, and that's what most of my work will have been done on for this presentation. So if I choose, we can also choose between ESI and APCI, so that gives us two options. One of the nice things about our instrument is we can actually use 6 masses or 5 masses in a mass range if you choose to do a cluster of ranges. I don't typically like doing the terminate on target, but I guess it has some uses. We can also view the MS spectrum in real time, just like I showed you with UV. So getting into mass detection, there are 4 factors that I like to at least focus on when I'm trying to do my method development and my purification and analysis. The first one I'm going to look at here is going to be adducts and fragments. Then I'm going to get into the method settings, hardware, and tuning. So one of the things that we have is we have a universal test mix, and it has 2 different compounds in it. The first one is going to be, the first peak is going to be 180. And the second peak is supposed to be a mass of 212. Frequently, when we wind up seeing this in our systems, we'll see the 180, but we'll see also a 211, 212, 221, some other individual masses. So when we also have this as well, which is the second peak, which pretty much mimics it. We're getting the plus 32, plus 41, plus 63. Quite a few may already understand these issues, but there's a lot of people that I've come across that actually are new to mass spec and don't really understand how to incorporate these things. They're just saying my mass isn't showing up. So I can't really help someone if they just say my mass isn't there, so I need a little bit more data. And this is typically what I wind up seeing, not just these, but in general, these are the most of the masses I see. You could also look at sodium adducts, chloride adducts, and some other stuff. So, but when we put in the universal test mixture, it makes it very difficult down here if we were to just test that mixture to see what masses we want to look for. So in knowing that, we can actually look at this and try and discern what might be the best options. In this case, ironically, even though we have 2 masses, some of these adducts might actually be the best options to do your detection. If we look into it, obviously you can see the acetonitrile for the 64 is going to be your acetonitrile plus sodium, but these are the ones that I see mostly. And the reason we're seeing this is we have a mobile phase that we're using to actually incorporate our sample into the mass spec after it's been diverted from your flow stream. That's going to be your methanol adduct because we're using methanol with a little bit of a modifier in there. Now, why did I also see acetonitrile? Well, I was running the chromatography with acetonitrile. So we could potentially have 2 different adducts because we're using 2 different solvents in the process of getting our compound from the injector over to the mass spec. So method parameters. So I'm going to go into that a little bit here. So if you go under your method development screen, you can actually do a lot of this, but we can also go into ionization settings. And I'll go into that a little bit later. But right now, if you look at this main screen, you'll see that we can do positive and negative. And we can also do things such as changing our individual ion settings between robust, typical, and fragile. These are the defaults that would come with the system. We can also come over here and choose detection ions. We can get an ion finder up here if you want to do certain things. The one thing that I want to look at that is most important that I run into most of the time, down here we can also see what we call fluid interface pressure. So this is where our modifier pump is actually, the pressure is being measured at the modifier pump as it's trying to introduce our samples into the mass spec. If this is not very stable, or if it's way down here on the lower left end, there's a possibility that you need to prime your modifier pump. So just to keep that in mind. The other thing that I'd like to let people recognize is that we can actually customize ionization settings. So if you have compounds that might be a little bit higher that don't seem to ionize well with the standard 3 options we have, we can define them and actually create your own custom ionizations. So I have a little video here of showing how we would actually choose your ions. There's a couple different ways we can do it. The simplest one is just go in here and actually click on the individual buttons and type them in one at a time. So then we would say, okay. Or if you want to do multiples, then we would just do the 180, say next. So weird seeing my hand going without me actually controlling it. Anyhow, so we'll go ahead and say close on that one. And so the other way is we can actually choose, sorry, that video got put in there twice. So as you can see right here, I'm just clicking on the individual ions and actually entering them in. So you can actually pull them directly from the screen as you're doing your ionization settings, which I find very useful. So we can do some optimization. And if you notice down here, this is our tune mix, or our test mix, I should say. You can see this is the second peak of it. So we're looking at 210 and 276. So there's the same clusters we were looking at earlier, and we're in positive ionization mode. You'll notice I've changed to 20 volts, and this is under our ionization setting, the third button down, third or fourth. So we can actually change it to 20, and all of a sudden, the 210 peak is starting to be a lot stronger and has a higher total response value. If we take it up to 30 volts, you'd think, okay, put more energy into it, and we should get better responses, right? Well, the red is where we were, and the blue is now where we're at. It's not anywhere near as good. So this is where we could actually create this off of the typical, and then save as, and create a new ionization pattern that we could use for our chromatography. The best way that I have found to actually get the best mass determination is to actually run a scout run. So this is something that we have in our software that is very standard to all systems. You don't have to have a mass spec, but this usually I would try and run this on a smaller column and then incorporate it into a larger column so we don't lose a large amount of material. But if we run a scouting gradient, we get a chromatogram. We can take that chromatogram, then pull up, in this case, remember how I mentioned we can actually choose your MS? So at the end of the run, we'd actually click on the MS button, look through here, and see which masses we would want to choose for that individual peak. So notice how we had 180 and 212, but we're not getting all these other masses up here anymore. When we've actually run the purification, it actually seems to do a lot better in getting us our main mass. So what I could do is then choose the 180 as opposed to those other masses up here that we were mentioning that might have been higher earlier. So when we do that, we can also go back then and choose a specific peak of interest based on a retention time, because we will also have our mass trace on here. I'm using someone else's slide for this, so that's why I don't actually have one with mass spec on here. But you could see the mass spec in the background and actually have that as one of your responses. And then we would choose the column of interest that we want to transfer this to, press focus. It'll generate a chromatography profile, grading profile, that is going to be optimized for that individual compound. When we run it, as you can see, we have a much greater separation across the entire run. The only caveat is we definitely have to have the scouting and the prep column as being the same medium. So some of the hardware factors that I've come across in the field, the source is going to be a big one. The interface over here, and I already mentioned that one a little bit, so I'm not going to go into the interface too much. And then, of course, the inlet and the capillary. So these are some things that we actually go into as far as what we would want to work on. So if we look at some of the positioning, you'll notice that this is in a high position, but there's no flow going right now. If I look over here, we have flow. Remember how I mentioned that I said that I didn't see a lot of pressure on the modifier pump? This would be one of the typical indications of that. You will not get a flow if you don't have pressure on the ionization, or on the modifier pump. So we can also adjust the location. Instead of just making sure we have flow, we can actually make sure that that flow is optimized for how we're introducing it into the source and into the cone of the mass spec. So if we adjust the ionization, or the capillary setting, notice how I'm doing that one-handed. I lost my videographer for the day, so all of these videos have been done one-handed, so I apologize if they're a little bit shaky. But we can also not just do up and down, we can also do forward and back. And you'll see in a second how that might actually affect things. So in the high front, we have normal ionization. We have a fairly strong signal, about 2.1 for this particular compound, which we're looking for at about 447. This one over here, we have totally different ionization parameters. Now, this is a 2 mix that we use. The higher masses are showing up a little bit higher when we're down in the low position. When we're up in the higher position, we're getting a lot more material in general. So this is one of the things that we want to focus on in your optimization for your method development. If we have the standard setting, which is what I was calling low, but it's really the standard default, we may be losing a lot of ionization and a lot of material because of the way it's being entered into the source. We can also change settings. So we can change the, remember how I mentioned we have the 3 options between typical, fragile, and robust. If we change to robust, this is actually in the probe position in the back, but it was such a low response that I had to actually increase to the robust setting and get a little bit higher ionization. Once I went and switched to the robust, then I was getting more response. So if we want to evaluate the source itself, this is how simple it is. So we basically have 2 clamps that we pull off on each side, literally doing it as one-handed, as I had mentioned. So we can pull out the inlet source, the flow from your mass spec or from your HPLC, pull that up, and you'll look at the cone right here, and that's one of the things that we like to keep an eye on, is the cone clean? Because if the cone isn't clean, you're going to get all kinds of background impurities, and you're also going to have problems with your ionization. So I'm going to go through a video over here of how simple it is to just take this out. It just screws off. There's a flapper valve, if you will, underneath the cone. So if you want to take that off and clean it, it's just that simple. What I would also suggest customers do is order an additional cone so that you can just basically pull one out, clean it at your leisure, and go ahead and replace it when it's clean. And it doesn't hurt your mass spec at all. We can actually, it's a no vent process. As you can see right here, this is something that we would need to clean because that is actually pretty dirty. This was actually prior to me putting that back on. I didn't clean it extremely well, but we do have a tool here to help us take it off. There are 2 notches here. You want to make sure that you don't damage them, but those 2 notches are so that you can put a wrench on it. Or if you haven't lost this already, go ahead and please use this because it makes it much, much easier to take the cone out. So now I'm going to get into potentially tuning the instrument itself. So if we tune the PurIon, this is one of the things that we're working on internally, but it's something that I want to make sure that you're aware of, that is something that you can do or ask about. This is the device that I typically use for tuning our mass specs on installation. This is also something that you could use as well. Most people that are doing mass spec are using something of this nature. It's just basically a standard syringe drive device. We can pressurize this one and introduce our sample. But one of the nice things about this, and I'm going to get to that in about a second or two, is on installation, this is how we actually set up our tune and our parameters for ionization. We can go down here and we can choose ESI, positive and negative, and APCI, positive and negative. This is great if you want to do a broad mix of compounds. You don't really have a specific region that you're looking at or a specific classification of compounds. We do have some customers who are actually choosing and putting in their own masses here. So instead of having these 5 standard masses, which is I think an Agilent 2 mix, but it's just a standard off-the-shelf mixture of components. We can also define this based on your individual compounds of interest. So if you wanted to tune and make sure that you're optimizing specifically for your individual compounds, we can do that. The other thing that I want to show you here is look at across the board, we're losing a lot of our high-end response. Now, if you look at this, it doesn't look horrible. I mean, according to the tune, it says, yeah, we passed. We're getting a response. But if we look at it and compare it to the low-end response, we're at about 174 to 1. To me, that's not a very good analysis. We have a very high resolution, first off, which is going to decrease our overall intensities across the board. Now, if I choose to use a slightly higher, I should say lower resolution, but a higher number, and sort of target a higher resolution by opening up, if you will, the window that allows more ions into our detector, we're going to get a broader band, but we're also going to get a higher intensity. So it'll actually get us up a little bit higher here, but you'll notice that the 922 now is all the way up around 14,600. We're around 24,000. But we're still seeing a huge discrepancy across the board of each of these individual compounds. So we can actually also do a custom ionization setup where we actually tune specifically based and optimize these individual values. And that would be changing these values over here. It's something we would suggest that you let us do as our service team would come in and either do a PM or work with you on this type of process, or our support team. Anyhow, as you can see, now we're getting a 65 to an 87 differential with about 100 to 180 in the middle. So we've switched our bias drastically towards the higher end, to the 600 to 900 mass range. And it'll help you be able to get your material off and have a higher sensitivity, higher response factor for them. So, having said that, I guess Sharon will take care of any of the hands or questions that you might have. So please feel free to, I'm just now pulling up some questions that I had. I'm so sorry. So that's a very good question. So the very first question is, what is 179 for a 180 compound? So the target on the mass that we get, the compound that we're using is specified as being a 180 mass, if you look it up in Aldrich or whatever. The difficulty with having just a single mass is the fact that, remember how I said we were at a 0.5 resolution all the way up to maybe a 0.7 resolution? We're going to be actually looking at a couple different things. So let me see if I can go back. So if I go back to one of the actual tunes here, my apologies, it was right here. So right there you'll have, this is where it's normally supposed to be. So normally if the instrument is tuned right, then it should be 180. We had such a wide range on our resolution, we were almost a full Dalton from side to side. So we're actually going to pick up 179 and a 180 at the same time, even though it is a 180 mass. So I hope that answers your question. I'll get to that. I'll go through them one at a time. What is the cause of the fluid interface pressure? Excellent question, Nancy. Nancy is someone who likes to check me all the time, and I appreciate it. So yes, one of the things that we would see is if we have a high pressure, obviously I mentioned low pressure or no flow. If we have an obstruction on our capillary going into the mass spec or the tubing, our instrument actually has a valve on the front of it so that we can actually introduce sample, so that you can actually see what material you're looking for before you ever actually run it. If any of those little components have a blockage in them, you're going to see high pressure there. Usually it's going to be in the tubing or the capillary itself that we put our line into. And how long do you have to wait when changing ionization samples between typical and robust? Usually it's pretty quick, Nancy. I would say maybe a minute or two is usually sufficient. The only differences between some of them, the fragile, I believe, takes the temperatures down to about 150 degrees. So we might be going from like 250 all the way down to 150. The voltages are instantaneous. You might want to give it a second or two to make sure that it's stabilized. But the biggest one that you need to focus on is waiting for the temperatures to stabilize for the heater block. And am I aware of a failed tune using the Adducts software? That is actually a very common question. The tunes could potentially fail. Why do they fail? Many different reasons. Usually, the ones that I have seen, it's because over a period of time, someone hasn't actually tuned for a very, very long time. So the mass alignment has drifted so far that we can't actually push it into the box. So we're basically trying to put a square peg into a round hole because we were too far from the window that we have set. So if I go back to the ionization parameters during our tune setup, so if you look here closely, you'll see that we actually have a window of about maybe 10 to 15 Dalton. So suppose that your drift is so bad that you tweak it, you tweak it, you tweak it, you tweak it, and we're just constantly redoing the tune to the point where we can no longer have that adjustability built into the quadrupoles. At that point, what it would require is probably cleaning, would be my guess. You could have our service engineers come in and do a cleaning and help you get back to getting a good response out of that. The other thing that might happen is that you don't have enough material going into your source. Do you have a blockage? Do you have a partial restriction? So if it's not actually seeing enough material or response, ionizations might not be strong enough for some reason. At that point, if you get a failure and it's not the cleaning, we might have to start looking at some possible failures in the hardware itself. Or, I've seen this too, maybe your tune solution's bad. We're actually running into that with the question of a bad batch, not something we provide, but someone was just using a tune mix that was not shipped properly from the factory, and it had some anomalies in it. So always just go back, maybe try another tune solution, see if you have anything that's a known good response, and then go from there. Are there any other questions? Actually, I guess we do have some. What is the expected flow of it? A very good question. So we actually have two different flow rates right now. I would like to optimize this a little bit more. So my role actually is more tech support and applications. So one of the things I'm trying to work on literally as I'm out here in Lincoln is coming up with some ideas for that. Right now, we use a 0.5 milliminute flow rate for the interface, and that's to make sure that we have a quick enough response time so that we don't miss material as it's going through the instrument. The other instruments that we have out there that are doing flash, the ACCQPrep and the NextGen, they both are typically running about 0.7, 0.8, and that's all controlled through the software. It's hidden. It's not something we can actually change. We can take these questions, of course, offline if you have some more further detailed questions or issues with that. But yeah, those are typically our two flow rates. It's 0.5 mils a minute and 0.7-ish. I think it's 0.75 or 0.7. I don't know the NextGen off the top of my head, but it's in that ballpark. Are there any other questions? Thank you all for your questions and for joining me today. If you have further questions, obviously, by all means. So let me see how the best way to reach me. My email is just Todd.Anderson at Teledyne.com. So by all means, send me an email and we can follow up. And we can take this and discuss a bunch of the other questions offline, obviously. Let's see. I think these will also be posted, and I don't know that I actually have my contact information. But the worst case scenario is just send us a link through our internal website, and they'll be able to get a hold of me pretty quickly, especially if you get a hold of me this week, because I'm still out here through the rest of the week. And then I can follow up with you later. Thank you all for coming. I think I've gone over a little bit, and I think I'm going to pass it now back to Sharon.
Well, thank you, Todd, for for presenting on this topic, and thank you for all that have submitted questions and attending the mass-directed purification. As mentioned earlier, it has been recorded and a video will be made available to you. As Todd also shared, if you have further questions regarding the webinar, please feel free to reach out to me through Zoom and I'll forward it on to the appropriate person. Thanks again for joining us and wishing you all a great day. Thank you.